Okay, so without further ado, let's start our class for today. So this will be our last module, okay, that will be covered in the final exams. Okay, and we have still having another module, module 10. Okay, if I have time, I will cover it. If not, I will just give the video for you to look at. Right, so for the module 9, okay, we're going to look at how to write a C programming for interrupt using the STM32. Okay, before we start with the write the programmings, okay, we are going to look at the introduction of the interrupt and exception. Right, so here is the overview of the interrupt. What is the interrupt? What is exceptions? Okay, it's actually interrupt and exception is the same things. Okay, usually, okay, interrupt is driven by event. Okay, which is you need to have a hardware such as the switches to trigger an event. So when the switches, the event is triggered, then after that it is called as a interrupt. Meanwhile, exception is still one of the interrupts, but it's triggered by a software. Okay, so use as example of the exceptions such as a port exception. Okay, when your program is crashing, okay, there will be a fault exception to stop the program uh, to run. Okay, and a part of that, other exceptions such as like timer exceptions. Okay, there are few exceptions actually in STM32. Okay, later we will see more detail about what the interrupt and the exceptions. But by rights, okay, interrupt and exception is the same things, right? So in a single microprocessor, okay, can serve several devices. Okay, means that you have a one processor, and this processor can have several devices to be served. Okay, to be execute. Okay, you can run a multitask at the same time, but there are to run this task here, several devices, several tasks. Okay, you need to have you need to have a methods to do it. Okay, so that tasks that have a higher priority will be run first, followed by the least priority task. Okay, so how to run? Okay, how the microprocessor serve these several devices at the same time? Okay, there are two ways to do that. First, we call it as by using the interrupts. Okay, and the second one by using a pollings. So what is the difference between interrupt and pollings? So for the interrupt, whenever a device needs a service, okay, the device notifies the CPU by sending an interrupt signal. So interrupt means that every time you're going the program or the device going to execute some tasks, okay, so it will give a interrupt signal to the CPU. Okay, upon receiving an interrupt signal, the CPU interrupt whatever it is doing and serve the device. Okay, means that when the interrupt signal is triggered, okay, CPU will stop the program that it is currently do. Okay, then after that it will go execute the that interrupt task or the interrupt programs. Okay, once the interrupt program is finished, then after that it return back to it returns back to the program that is previously stopped and continue with that programs. Okay. Meanwhile, for the polling, the CPU continuously monitor the status of the given device. Okay, when the status condition is met, it performs the service. Okay, after that, it move on to monitor the next device until each one is serviced. Okay, compared to the polling and interrupt is an event driven. Meanwhile, polling is time driven. So that's why by using a polling, okay, the CPU need to keep monitoring, okay, whether there is a program need to execute. Okay, if the program is need to execute, then after that it will go to that program, okay, to okay, to perform the task. Okay, so by using a polling means that, okay, your CPU will keep busy monitoring, okay, any uh, uh, status, okay, where you're going to check lah the status of the condition, whether it's met or not. Okay, if it is met, then after that it will execute a programs. Right, so now we're going to look more details on the interrupt and polling. So interrupt is a hardware or software signal, okay, that are temporarily halts the execution of the main program, okay, and to execute the ISR. ISR means that interrupt service routine, okay, which is the program that need to be executed by the CPU whenever the interrupt is triggered before returning to the main programs, okay. So this mechanism is an event driven, okay, which is processor only respond to the event as they occurs. Okay, as I mentioned earlier, interrupt is event driven. Okay, whenever the interrupt signal is triggered, the CPU, okay, will stop whatever it is currently doing, okay, which is the main program. Okay, we have a main program, we have the interrupt service routine. Okay, the CPU currently run on the main program, and suddenly the interrupt service routine is triggered. So what happens? The CPU will stop the main program. Then after that, execute the interrupt service routine. After the interrupt service routine is finished, then after that, it will return back, continue the main programs. Okay, there are three types of interrupt in a Cortex-M processor. Okay, first we call it as a external interrupts. Okay, which is a external interrupt is triggered by external signal such as switches, button whenever you push a buttons. Okay, the second one we call it as an internal peripheral interrupts. Okay, so this internal peripheral interrupt will be triggered by on-chip peripherals such as timer overflow. Okay, UART data receive. Okay, when you do a serial communications. Okay, when the serial communication is finished. Okay, when you're going to send the data on the communication lines. Okay, when the data is finished, when the CPU finish sending the data, okay, so the interrupt will be triggered. Or ADC conversion, okay, whenever the ADC conversion is complete, then it says that, okay, now we're going to trigger an interrupt saying to the CPU, okay, we already finished, okay, do the data conversion, the analog to digital data conversion. Okay, and the third one is called as a software interrupt or exceptions. Okay, so every time an interrupt done, okay, triggered by a software, okay, you can call it as a exceptions. Okay, so examples of the exceptions is triggering an interrupt by program execution error. So every time the program execution got errors, okay, the fourth exception will be triggered, saying that, okay, we have an error, so, okay, we need to stop, okay, you need to debugging the error so that after, okay, so that the error will be resolved, then after that you can run again the program. So here we're going to look at how the interrupt works. Okay, so when an interrupt event occurs, okay, when you trigger an interrupt, the NVIC, so NVIC stand for Nested Vector Interrupt Controller, receive that interrupt signal. Okay, once the NVIC receive the signals, okay, it's tell the CPU, okay, now you need to suspend the current instruction. Okay, you need to suspend the main programs. Okay, whatever that you currently do. Okay, and upon suspending the main programs, okay, the CPU will save the program state onto the stacks. Okay, so it will save the program counter, register, link register, whatever value that you think that is very important, okay, will be stored inside of the stacks memory. Okay, once finished, okay, do the context savings, Then after that, it will jump, the CPU will jump to the ISR, the interrupt service routine. Okay, and the CPU will execute the interrupt service routine. Once the ISR is executed and finished, the processor restore its previous state and resume the main programs. Okay, so we can see from this figure down here. Okay, so we have the main program here. Okay, the running programs, the main programs. Okay, suddenly interrupt is triggered. So what happened for to this main program? Okay, this main program will be paused. Okay, will be stopped. Okay, and at the same time, the CPU will save the program state to the what we call here, to the stack memory. Okay, once the contact saving is done, then after that, it will go, the CPU will process the interrupt. Okay, do the task, whatever task under the interrupt service routine. Once finished, okay, once the ISR is finished, then it will restore the states, okay. It will get the contents that been saved earlier in the what we call here, in the stack memory, and put it, okay, to the original registers, and then resume back the current the running program or the main program. So this is what happened when interrupt is triggered. Okay, next moving on to the pollings. Okay, we're going to look at how the pollings works. Okay, so polling is a technique, okay, where the processor continuously monitors, okay, a peripherals or input by repeatedly checking the status in a loop. Okay, by using a polling, the processor will get busy. Okay, it needs to monitor, okay, whether the it needs to perform the task or not. Okay, so this mechanism called a time driven. Okay, it's a time driven. Okay, the program explicitly asks whether an event has occurred or not. Okay, so here in this examples here, in this figures, we can see the difference, okay, between interrupt and polling. Okay, when using an interrupt, you can see here you have the CPU, okay, and then GPIO. Okay, GPIO is the one that we're going to call an interrupt. Okay, we'll be triggering an interrupt. Okay, we call it as a external interrupt. Okay, so the CPU, okay, while waiting the interrupt be triggered, okay, the CPU will do nothing. Okay, then the CPU do nothing when the interrupt is triggered here. Then after that, the CPU will go to the interrupt service routine and process, okay, everything, okay, the interrupts under the interrupt service routine. Okay, compared to the pollings, okay, at the bottom figures here, okay, we can see here, the CPU keep monitoring for the GPIO. Okay, okay, first, okay, do nothing, then after that, check the GPIO, whether the switch is triggered or not. Okay, if not, then it go back, okay, okay, still waiting for the what we call here, do nothing. Then after that, it will check back the GPIO state, whether the GPIO asking, okay, to do a polling or to do a certain task or not. Okay, and it will keep repeating, okay, until, okay, the GPIO says that, okay, I'm ready, okay, to give a data or to read a data. Then after that, okay, the CPU will go, okay, execute that programs. Okay, so that is the two different things between the interrupt and polling. Okay, the interrupt you can see here, the CPU, okay, do nothing. Why? Polling, the CPU keep busy monitoring the status of the GPIO, whether the GPIO is ready to receive or to ready to give the data or to read the data. Okay. So this is the apa ni kita panggil the comparisons lah, okay, between the interrupt and pollings. Okay. The interrupt is an event driven. Okay, means that okay, you press the button, then okay, the program will be automatically executed, while polling is time driven. Okay, the CPU checks the status. If the status is met, then after that it will go lah to the execute the program. If not, okay, it will keep monitoring. Okay. In terms of efficiency, okay, CPU, okay, will sleep or works on other tasks while waiting for the interrupt to be triggered. But polling is inefficient. Why? Because the CPU constantly check for the event to occur. So the CPU cannot do anything. Okay, compared to interrupt, the CPU can do other programs. The CPU can either do other programs or just sleeps, okay, to preserve power consumptions. But in polling methods, okay, the CPU must keep busy to check the status, okay, of the GPIO, whether the GPIO is ready to send the data or to receive the data. Okay, in terms of the response times, okay, using the interrupt is an immediate, okay, and it is depend on the interrupt priority. Okay, why polling is a delay? Okay, depend on how frequent you check. Okay, you check the data. Okay, when to check to monitor the data whether the data is ready or not. Okay, so this is where the CPU checking for the data. Okay, it's asking the GPIO, are you ready? Send the data or read the data? Not ready. Okay, check again after a few seconds. Okay, are you ready or not? Okay. So depending on how frequent, if you have a very frequent, then after that, okay, it will the response time will be quick lah. But if you if you're going to check, monitor, okay, with a with the longer frequency, okay, then after that, okay, it will got a delay, okay, in terms of the response time. Okay, in terms of the implementation, okay, for interrupt is complex lah. Okay, which is you need to enable the interrupt service routine. Okay, you need to set up for the NVIC and so forth. Okay, but polling is very simple. Okay, you just use loops, okay, to check the status. Okay, keep monitoring. Okay, use loop, okay, to check the status of the GPIO, whether the GPIO is ready to give a data or to send the data. Okay, power consumption, in terms of power consumption, interrupt use a very low power consumption. Okay, okay, why? Because okay, it can still waiting for the interrupt to be triggered while it is under the sleep mode. Okay, compared to the polling, requires high power consumptions. Okay, because the CPU is active during polling. Why? Because it need to keep monitoring the status. Okay, the status of the GPIO, so that it will keep busy. The CPU will keep busy, and then hence it is consume more power. Okay, and then next we are going to look at the interrupt. What are components that are important in interrupt? Every time you're going to do an interrupt, okay, these are the components that you need to look at. Okay, the very first thing here is the interrupt service routine, the ISR. The ISR, or interrupt handler, is a program that executes to perform a certain service when an interrupt occurs. So ISR is actually a program that need to be done every time the interrupt is being triggered. Okay, so here you can see here from this what we call figures. Okay, from these figures, okay, we can see, okay, we have a very few type of interrupts. Okay, the first one here, the interrupt that coming from the peripherals, okay, such as the what we call switches, okay, from the GPIO, okay, so that's why we call it as a IRQ, the interrupt request. Okay, so This is where you're going to put to your GPIO pin. Okay. Then we have the NMI, the non-maskable interrupts. Okay. And this peripheral, okay, will connect to the NVIC. Okay, NVIC is actually what we call a brain. Okay, a controller. Okay, which is control. Okay, how to perform the interrupt. Okay, it will determine. Okay, which interrupt will be executed, because the NVIC will select the interrupt with a higher priority. Okay, will be served compared to the interrupt with the lower priority. Okay, so here, what happened here is when the signals are triggered, okay, by using the IIQ, okay, the IRQ, the interrupt request, okay, IRQ is stand for the interrupt request. Okay, when the signal are triggered by the IRQ, CPU, okay, push the program counter register onto the stacks and load the PC register with the address of the interrupt service routine. Okay, so this will cause the ISR to be executed. So every time, okay, the interrupt triggered, what happened here is, okay, this program counter, okay, will get the address of the ISR, okay, from the vector tables. Okay, then after that, after get the address of the ISR, then it will jump to execute that interrupt service routine, okay, to execute the ISR. Okay, next we're going to look at the nested vector interrupt controller. Okay, as I mentioned earlier, okay, so this nested vector interrupt controller is the brains lah. Okay, it's a controller to manage all of the interrupts. Okay, so NVIC is used to handle an interrupt management. Okay, including the prioritizations. Okay, which interrupt will be executed. Okay, depending on the priority of the interrupts. Okay, and masking an interrupt means that, okay, it will block any interrupt from being executed. Okay, and dispatching enabling efficient and flexible interrupt and links. Okay, so as the name suggests, it supports the nested interrupt. What is a nested interrupt? Okay, we have previously we have the nested subroutine. Okay, nested interrupt is similar to the nested subroutine lah. Okay, which is interrupt inside interrupts. Okay, meaning higher priority interrupt can preempt lower priority interrupt. Okay, let's say lah. Okay, first main program. Okay, the CPU, okay, currently execute the main program. Okay, we have the main program here. Okay, then after that, one interrupt is being triggered. Okay, so this interrupt here, ISR with the priority 7, for example. Okay, the priority of the interrupt depending on the, okay, how small the number is. The small number of the ISR will have the higher priority. Okay, so ISR 7 is triggered. So what happened? The main programming will be stored. Then ISR 7, okay, will be executed. Okay. In the middle of ISR 7, then another interrupt triggered, which is ISR 1, the interrupt service 1. Okay, the interrupt service 1 have the higher priority compared to the interrupt service 7. So what happened here? The ISR 7 will be stopped, then ISR 1 will be executed. Okay, so this is what happened inside of the nested interrupt. Okay, the interrupt with a higher priority can preempt the lower interrupt. Okay, once the ISR 1 is finished, then after that, okay, the CPU will continue with the interrupt service routine 7. Okay, once the interrupt service routine 7 is finished, then after that, it will continue back to the main program. Okay, so this is how the nested interrupt works. And here, in this figure here, okay, there are various sources of exception or interrupt in the STM32 microcontroller. Okay, we have the NVIC. Okay, so the interrupt can come in from the peripherals, okay, which is we call it as a IRQ. The IRQ can be from the IO port, okay, you're from the GPIO, okay, can be from the peripherals such as the USART, ADC, and etc. And then the interrupt also can come in from the SysTick timer. Okay, this one we call it as a timer interrupts. Okay, and last but not least is a system exception. Okay, the exception that triggered by a software. Okay, if a port happen, okay, if the program is currently got an error, so the port exception will be triggered. Okay, so there are various sources of exception or interrupts that can trigger, and the NVIC will manage, which interrupt need to be executed and which interrupt need to be masking. Okay, moving on to this slide here. Okay, in Cortex M4, okay, NVIC support up to 240 interrupt requests. Okay, a lot of interrupt requests. Okay, available in STM32 Cortex M4 processor, up to 240 interrupt requests. Okay, non-maskable interrupt. Okay, so this is non-maskable interrupt. Okay, the interrupt that cannot be maskable. Okay, SysTick timer interrupts, and a number of system exceptions. So this is a system exceptions lah. Okay, this is the SysTick timer. Okay, and then the IRQs. Okay, so most IRQ are generated by peripherals such as timers, okay, IO ports, communication interference such as UART, I2C, ADC, and etc. Okay, now we are going to look at the exception types. Okay, the interrupt types. Okay, so exceptions are numbered from 1 to 15 for system exception. Okay, you can see from this table here. Okay, from 1 to 15, this one we call it as a system exception. Okay, so system exception, this thing lah. Okay, this is a system exception. Okay, and number 16 and above, okay, for the interrupt input. Okay, we have when the number of interrupt, the number of the exception is 16 and above, we call it as it's at the interrupt input. Okay, so the red color here, this is for the exception. The blue color is for the interrupts. Okay, most of the exception and interrupt have a programmable priorities, and a few system exception have a fixed priority. Okay, you can see here in this row, in this column, okay, you can see the priority of the interrupts. Okay, there are fixed priority, okay, which is -1, -2, -3. Okay, we already learned about it in the what we call it, in the PES-free register, in the non-maskable register, okay, previously in module 4 or 5. Okay, there are 3 exceptions that have the fixed priority, okay, which is a hard port, non-maskable interrupt, and a reset. Okay, the one with the lowest numbers got the highest priority. Okay, meanwhile, okay, other interrupt and what we call here exception, okay, the priority is configurable. Okay, you as a programmer can configure, okay, what would be the priority level. Okay, which one can have the higher priority and which one can have a lower priority. Okay, so here we can see here, okay, we have a total of 15 exceptions. Okay, started with the reset, NMI, and hard fork. Okay, so this three is very highest one lah. Okay, because the priority is in a negative priority. Then we have the memory management, bus fault, usage fault, SV call, debug, okay, SysTick, and man SV. Okay, the function you can read it at the last column here. Okay, what will be the functions? And then next we have the IRQ. Okay, IRQ is actually the interrupt request. Okay, so now we are going to look at this IRQ. Okay, the interrupt request, how to configure the priority of the interrupt request. Okay, how to do a setup, okay, in order to to make sure that every time you push this button, okay, the interrupt can be triggered. Okay, before that, okay, we're going to look at this vector table. Okay, so the vector table is actually a data structure located at a fixed address in a memory. And this vector table contains the starting address, okay, or sometimes we call it as a pointer of the exception, handlers, interrupt service routine, and the initial state pointer. Means that inside of the vector table, okay, it will have the address of the exception. Okay, so you have a total of 15 exceptions. Each of these exceptions will have its own addresses, as well as the interrupt request. Okay, the interrupt request also will have its own addresses. Okay, so all of these exception and interrupt addresses will be stored inside of this vector table. So that's why every time the interrupt or exception triggers, the program counter know, okay, now this interrupt is being triggered. How they know? Based on the address of that interrupt or the exception that is located inside of this vector table. Okay, so when exception or interrupt occurs, okay, whenever the interrupt is triggered or exception is triggered, the processor use the vector table to locate the appropriate handler and jump to its address. So, okay, so when the interrupt is triggered, program counter will find out, okay, which exception is triggered. Okay, once it will get the address, okay, of that exception or that interrupt, and then jump to that ISR to perform the task, okay, to execute the interrupt service routine. Okay, so the vector table is organized as follows. Okay, you can see here at address 0, this is the MSP, okay, the initial main stack pointer. Okay, the first entry in the initial value of the stack pointer at the system start up, and then you can see next followed by the reset vector, NMI, hub port vector, memory managed vector, bus port, usage port, and when you're going to use the interrupt service routine, the IRQ, okay, the IRQ will be stored at these addresses. Okay, if you can see here, okay, the way they store the address for each of the exception depending on the exception number. Okay, you can see reset will be stored first after the main stack pointer, followed by NMI. Why? Because you can see from this exception type, NMI will be the second lah. The second have the second in the table of the exception. Okay, then followed by hub port, memory management, bus port, until IRQ. Okay, the IRQ will be the last one, okay, which is located from this address. Okay. So that is the introduction on the interrupt. Okay, any question up until here? So in this module here, okay, we're going to cover on this IRQ, okay, how to trigger an interrupt using the external hardware, okay, interrupt, which is triggered by using a switches or triggered by using the sensors. Any question, guys? Okay, if no question, then we move on to this slide. Okay, before that, okay, I'm going to ask you to, at the same time, okay, I'm going to ask you to sign the attendance, okay, by click the link I provide in the chat box. Okay, now moving on to the external interrupt. Okay, external interrupt. Okay, we only cover for the external interrupt. Yeah? Internal interrupt such as the USART, okay, ADC will not be covered, as well as the software application. Okay, we're only looking at the external interrupt. Okay, the one that triggered by using the GPIO, the switches that you put that you connected to the GPIO, or a sensor that you're going to put it on the GPIO. Okay, so this is the introduction on the external interrupt. Okay, so every time you reset your microcontroller, okay, all interrupt are disabled. Okay, why disabled? Because, okay, if you recall back, every time you switch off your microcontroller, all the value inside of the register, okay, the memory, okay, the peripherals memory, data memory will be erased. Okay, so the default value will be 0. Okay, so that's why all interrupts also are disabled. Why is that? Because interrupt is located, okay, the interrupt register is located under the peripheral register. Okay, we already learned in the previous module, okay, module 8. Okay, so to active an interrupt, okay, you need to enable the interrupt. Okay, there are two locations that you need to enable the interrupts. Okay, the very first location here is you need to enable at the peripherals modules. Okay, at your GPIO. Okay, so that is very first thing that you need to enable the interrupt. Once you finish enable the interrupt at the peripheral module, then after that, we are going to enable the interrupt on the NVIC module. Why NVIC module is needed? Okay, you need to enable the interrupt in the NVIC module as well. Why? Because NVIC will manage the interrupt. Okay, which one will it will manage, okay, how the interrupt, the behavior of the interrupt based on the priority. Okay, it will allow, okay, the interrupt with a higher priority, okay, to be executed, okay, while the interrupt with the lower priority will be put under the what we call here, okay, waiting mode. Okay, once the interrupt with a higher priority is finished, then after that, the interrupt with the lower priority can execute. Okay, and all I/O pin of the STM32 may generate an external interrupt. Okay, we have a total of port A 16 pin, port B, okay, we have 15 pin, port C 16 pin, port D also 16 pin. Sorry, port D is 1 pin. Okay, so all of these pin in STM32, okay, especially in the Nucleo 64 board, okay, you can use it as an external interrupt. Okay, you can generate an external interrupt. Okay, to use the external interrupt lines, okay, the port pin must be configured in input mode. Okay, why input mode? Because we're going to connect that, we're going to trigger the interrupt by using a switch, by using a sensor. So that's why it needs to be configured as a input mode. Okay, how to configure the GPIO as an input mode? Okay, you can configure it at this register here, the mode register. Okay, make sure that you make it as a input mode. Okay. Okay, so each of the EXT I0, okay, external interrupt 0 to external interrupt 15, okay, is assigned to a group of a IO pin. Okay, we have a total of ESTI0 until ESTI15. Okay, so ESTI0 will be triggered by the line 0, okay, whether it's from PA0, PB0, PC0, PD0 until PH0. Okay, every time the what we call here, you press a button, you connect a button to PC0, okay, the pin 0, okay, to all the GPIO port, any of the GPIO port of the pin 0, okay, so it will fall under the external interrupt line 0. Okay, if you put your switch or your sensor to trigger interrupt at PA15, for example, then after that, it will fall under the external interrupt line 15. Okay, so all the PX0, PA0, PB0, PC0, until PH0 lah, pin are grouped together and fed to external line 0. Okay, contoh. I give you a contoh. Okay, I'm going to put a switch at PC10. Okay, I have a switch to trigger interrupt on a PC10. So my interrupt here called as a EXTI10, external interrupt line. Why? Because located at pin number 10. Okay, so since STM32 have up to 60 pin for each port, okay, as we learned in the previous module, okay, therefore there are a total of 16 external interrupt lines started from EXT I0 until EXT I15. Okay. So this is the figures of the external interrupt lines. Okay, you can see here. This is a EXT I0, external interrupt line 0. Okay, so all of the external interrupt line 0 is coming from this pin here. Okay, whether it's from the PA0, PB0, PC0, PD0 until PH0. So all the pin 0 are grouped and called as a external line 0. Okay, external interrupt line 0. Okay, meanwhile, okay, if your pin is connected to pin 0 from P, whether it's from PA, to pin 10, whether it's from PA10 until PH10, that external interrupt will be called as an external interrupt line 10. Okay. And of course okay, if you have the pin, okay, that is coming from the pin 15, that external interrupt will be called as an external interrupt 15. Okay, so although multiple pins are mapped into a single external line, but only one can be source of the interrupt. Okay, you can see here, okay, from here, we have a total of 8 pins, okay, that are mapped to external line, interrupt line 0. Okay, even though you have 8 pins, okay, only one pin can be source of the interrupt. Okay, if you connect the switch to trigger an external input, external interrupt line 0 to the PA0, for example, okay, PB0 until PH0 no longer can be used to trigger an external as an external interrupt line 0. Okay, only one pin, okay, can be used to as a source of the interrupts. Okay, for examples here, okay, cannot define both PA0 and PB0 as an input interrupt pin for external interrupt line 0. Okay, so if you choose PH0 as a input for the external line interrupt 0, so the other pin will be cannot be used. Okay, you can void other pin. Okay, and the port pin that will be responded to is selected by a multiplexer using a bit from sysconfig external interrupt control register. Okay, so we will be using this register here, okay, to config, okay, which port pin, okay, that will be respond every time the interrupt is triggered. Okay, there are 4 external interrupt control registers, okay, which is ESTICR1, ESTICR2, ESTICR3, and ESTICR4. Okay, later we'll see more detail on this ESTICR register. Okay, there are few registers that you need to know okay, before you can write the program for the interrupt. Okay, one of them is this sysconfig ESTICR register. Okay, so here, now we're going to look at this register here. Okay, what this sysconfig ESTICR register do? Okay, so each register of a ESTICR X, okay, will handle a 4-bit to select from up to 8 possible port. Okay, 8 possible port meaning that this port okay, each of the external interrupt lines will have up to 8 port. Okay, only one port can be used, okay, to trigger an interrupt. Okay, once that port used as to trigger interrupt, the other port will be void. Okay. So here, okay, let's look at the sysconfig external interrupt configuration register 1. Okay, you can see here. Okay, so from the 32-bit, only 16-bit that you're going to look at. Okay, the first one, bit 0 until bit 3. Okay, so this is for the external interrupt line 0. Okay, so ESTI 0, okay, we're going to configure at this bit lah. Okay, then followed by external interrupt line 1, okay, from bit 4 to 7. After that, we have the external interrupt line 2. And last one is an external interrupt line 6. Okay. Okay, if you connect your switch to external interrupt line 4, okay, so next you need to configure at this register here, okay, called the sysconfig external interrupt configuration register 2. Okay, and then this is for the ESTI 5, ESTI 6, and ESTI 7. Okay, so we have how many total of external interrupt lines? We have a total of 16 external interrupt lines, okay, from 0 to 15. Okay, so from external interrupt 0 to 3, okay, we'll be using the ESTI CR1. Okay, external line 4 to 7 will be using this external interrupt configuration register 2. Okay, meanwhile, if you going to use the ESTI 8, okay, until 11, okay, you're going to configure at this ESTI CR3 register. And last but not least, okay, if your switch, okay, is connected to either to external interrupt line 12 to 15, then after that, you're going to use the ESTI CR4. Okay, so how to configure? Okay, to configure here, we're going to refer to this table here. Okay, let's say lah. Okay, I have switches. Okay, that I need to trigger an interrupt. Okay, and this switch here, I connect to PC12. Okay, so for the PC12, the external interrupt lines that I need to use here is EXTI 12. Okay, for the ESTI 12, where I'm going to configure the ESTI 12 so that it can trigger and interrupt. So for the ESTI 12, I need to configure at EXTI CR4. You can see here, this is where the ESTI 12 is located. Okay, under the ESTI CR4 register. Okay, so what value that I need to put here to configure here so that PC12, okay, can be used to trigger an interrupt. Okay, so now once we are identified, okay, what is the external interrupt lines and what are the registers, the sysconfig register that we're going to use, then after that, okay, we're going to configure by referring to this table. Okay, this table here. Okay, now we have a PC12, okay, port C. Okay, for the port C, okay, the configure value that we need to configure is, okay, we're going to look at here. Okay, you can see PCX pin. Okay, X means that, okay, tak kisahlah whether pin 0, pin 1, pin 2, or pin 15. As long as it is coming from port C, okay, the value will be 0, 0, 1, 0. Okay, so this will be the value that I need to configure to the sysconfig external interrupt configuration register 4. Okay, how to do it? Okay, later we'll see lah how to write the program. Okay, so that PC12 can be used to generate an interrupt. Okay, if you not configure the sysconfig external interrupt configuration register 4, what happens when every time you press this switch here, the interrupt will not triggered because the CPU, okay, because we don't enable we don't configure the what we call here this PC12 as the external interrupt 12. Okay, so what happened? The interrupt will never be triggered. Okay, so this PC12 will be act as a normal switches, not the interrupt switch. Okay, so that's why you need to configure to configure. Okay, to configure the sysconfig external interrupt configuration to registers so that the PC12 now can use as to trigger and interrupts. Okay, so that is the very first register that you need to know. Okay, the sysconfigs. Okay, EXTI configuration register. Okay, next the second one. Okay, the second one, the second register that you will need to configure is RCC APB2 ENR. Okay, I think you already recall the bell. Okay, previously we enabled the RCC AHB1 ENR. Okay, so this is similar, quite similar, which is you're going to enable the clock for the peripherals. Okay, since we are going to use the interrupt, okay, so we need to configure the APB2 ENR. Okay, why? Because to use the interrupt to make this port as a interrupt, okay, to trigger interrupts, okay, we need to configure at this register. Okay, so hence we need to enable the sysconfig so that we can use it to trigger an interrupt. Okay, so what would be the bit that you will need to look at whenever you're going to enable the interrupts? Okay, we only focus on this bit 14 only. Okay, you can see here bit 14 is for sysconfig enable. Okay, to enable the sysconfig. Okay, so that's why we need to put 1. Then after that, okay, this sysconfig can be used. Okay, once the sysconfig can be used, then the PC12, okay, after we put this number here to this sysconfig, okay, ESTICR4, the PC12 now can trigger an interrupt. Okay, so this is very important. Okay, so we need to enable, okay, the sysconfig at what register? APB2ENR register. Okay, so let's look at this programming. Okay, examples. Okay, configure the sysconfig XTICRX if PC13 to generate an interrupt. Okay, so we have a switches. Okay, and this switch is connected to PC13. Okay, so what we need to do? Okay, first step. Okay, enable the sysconfig. Okay, so RCC APB2 ENR. Okay, what value that you need to give here? Okay, so here, since we are going to enable the sysconfig, okay, the value we need to give is 0. Okay, the rest will be 0 lah. Okay, only bit number 14 will get 1. Okay, the rest of the bit will get 0. Okay, the value is always 4000. Okay, so 0x4000. Okay, so this is the default value. Okay, every time you're going to enable the interrupt, okay, to enable the sysconfig, that is very first things lah. Okay, to enable the sysconfig, the default value should be OX4000. Okay, once we enable the sysconfig, then after that barulah kita make the PC13, okay, to act as a interrupt port. Okay, the interrupt input. So how to do it? Okay, we need to enable, okay, do a some configuration at sysconfig EXTI Okay, what CR? Okay, if you go back to ESTI's CR, okay, pin 13 is actually at this location. Okay, under ESTI's CR 4. Okay, so this just now is a PC, port C. So what number that you need to give here? Okay, based on this, what we call a table here, okay, for the port C, the value that you need to give is 0010. Okay, what about the rest? The rest you just give 0 lah. Okay, so the rest just give 0. And when you change it to a hexadecimal, okay, you will get 0020. Right, so here equal to 0x0020. But, okay, don't forget to put the, if you put 4 here, wrong, because this is an array. Okay, if you see the bracket here, the bracket means an array. Right? So here, okay, we know that we have a total of EXTICR, okay? EXTICR1, EXTICR2, EXTICR3, and EXTICR4. Okay, we have a total of 4 ESTRs. And all of this ESTCR is actually located, okay, stored inside of an array. So that's why this is ESTICR 1 is located at array 0. Okay. This one is at array 1. ESTICR3 is at array 2, and ESTICR4 is at array 3. So that's why you can see here the value that you need to put under the bracket here. Okay, this bracket is not 4 but 3 because it is located, okay, on the third array, the ESTI. Okay, then that's it. Okay, this is how we're going to enable. Okay, this is for only to enable the pin, so that the pin, okay, the GPIO pin can act as a interrupt pin. Okay, the rest, okay, later we'll continue, sir. Okay, with the others. Okay, so I think we just stop here. Any question up until here? Ada soalan tak from you guys? Okay, so if no question, I think we'll stop here. All right, thank you guys, and